So mass is directly proportional to Q, mass is directly proportional to I, mass is equal to ZQ, M is equal to ZIT, Z is equal to gram equivalent weight by Faraday, Z is equal to M by NF, therefore M is equal to M by NF into IT. Then second law, Faraday's second law, let us consider three different electrolytic baths where we have nickel dipped in nickel 2 plus ion, that is nickel sulfate, copper dipped in copper sulfate, cobalt dipped in cobalt sulfate. And we know very well, by passing the same current for the same passage of time passage, now we have, this is proportional to the electrochemical, that is MNI, mass of nickel deposited will be proportional to the electrochemical equivalence of nickel. Similarly, mass of copper is proportional to electrochemical equivalence of copper, and the mass of cobalt is proportional to electrochemical equivalence of cobalt. Now we can divide this and we can get the constant. So MNI, mass of Ni divided by mass ZNi, that is also equal to mass of copper divided by the respective chemical equivalence, that is electrochemical equivalence of copper. And as you know, that is, if it is a nickel, then what is the electrochemical equivalent of nickel, which is nothing but gram equivalent weight of nickel divided by the valency factor. Gram equivalent weight means its atomic weight, the atomic weight of nickel divided by the valency factor is 2, and F is 96,500 coulombs. So you can make it as ZNi. So these things are constant. So it means either you can take this, you can interchange this MNi divided by MCU. This Ni can be brought here, therefore ZNi divided by ZNi. So from this it's clear that mass of nickel divided by mass of copper is always a constant. That is, mass of any metal divided by its mass of, in this case, that is Z. Okay, that is, this is mass. So mass of another metal, that is M1, M2. It is always constant because this is proportional to electrochemical equivalence ratio. So this is regarding Faraday's law of electrolysis. And then let us discuss a problem based on Faraday's first law, where I got the silver nitrate solution, and that is electrolyzed for 20 minutes. So the time is 20 minutes with a current of 2 amperes. Calculate the mass of silver deposited at the cathode. So the mass of silver deposited is asked here, and the given are electrolyte is AgNO3 solution, and T, the time of passage of currents, is 20 minutes, that is equal to 20 into 60 seconds, where I is equal to 2 amperes. So we have to calculate mass of silver deposited at the cathode. So we know the equation M is equal to ZIT. So gram equivalent weight divided by Faraday into IT, and which is nothing but molecular weight of silver divided by the valency factor of silver in this reaction into F into IT. So when you consider this equation, in fact the number of electrons transferred is only 1. So we can consider in this case, that is mass of Ag, which is nothing but 108 divided by, that is atomic mass, molar mass or atomic mass of silver is 108 divided by number of valency is 1, that is valency factor, number of electrons transferred, and 19,500 coulombs, that is a Faraday, into 2 into 20 into 60. So we are able to get 2.68. So this is the way you have to calculate the that is the mass of silver deposited. So likewise, based on Faraday's law, you can expect various strategies here. For example, M is equal to ZQ. So they may provide Z and Q and ask M. Otherwise they will provide M and Z and you will be asked to find out Q. Similarly, sometimes you will be given IT and M, you have to find out Z. Otherwise all these factors will be given, you have to find out M. So M is equal to Z. And in this case M is equal to molar mass divided by NF into I into T. So they will give molar mass I, T, and also N, F, you have to find out the mass deposited. Otherwise, mass will be given, and you may be asked to find out the current passed also. So likewise, you can interchange this. Then Z is equal to M by NF. Similarly, Q is equal to IT. So, and this is based on second law. Ma by two different metal mass ratio is equal to their equivalent ratio. So based on that, they will give. For example, they will give the mass deposited of one electrode, that is one atom, and equivalent mass will be given, and equivalent mass for other metal will also be given, but you will be asked to find out what is the B, mass of metal. So likewise, you have got Ma divided by Mb, that is equal to Za divided by Zb. So based on that, you can anticipate. Similarly, you got this equation, and as I already mentioned, based on electrochemical equivalence, you will expect some questions. Then Kohlrausch law of independent migration of ion. See, that is when you describe this Kohlrausch law, you have to add this independent migration of ion. That is very, very important. So the equivalent, for example, let me consider sodium chloride. Sodium chloride is an univalent strong electrolyte. In this case, it will readily ionize as Na plus and Cl minus. So the molar conductivity at infinite dilution for NaCl can be predicted by sum, that is adding the ionic conductance at infinite dilution of the respective ions involved here. But in the case of that is a weak acid, this is not feasible, because let me consider acetate, sodium acetic acid. So the acetic acid is not readily ionizable. It's not completely ionized. So you cannot employ this equation directly. Similarly, in the case of a weak base. So what we are going to do is, before that you should try to understand, when I put capital letter lambda, that indicates the conductivity, molar conductivity. When I put not, infinite dilution. When there is no not, that is at certain concentration. So we all deal with the infinite dilution only in the case of Kohlrausch law. So the molar conductivity of any ion which is readily ionizable is nothing but the sum of the concerned or the participating ions molar conductivity. This is ionic conductivity, that is cationic conductivity, anionic conductivity. So when you calculate this, you have to consider the crisscross method also. For example, let me consider AXBY as compound, as salt. So what is the oxidation state of, or the valency of A by crisscross? You can say it is Y. So you can mention this as A plus Y. Similarly, for B, you have to consider this X, so minus X. As in the case of sodium sulfide, where you can find sodium, what is the valency? Plus 1. So you can put plus 1. What is the valency of sulfur? By crisscross method, this is minus 2. So likewise, you should have the general representation like this. Therefore, AXBY is equal to, there are X number of moles of A plus Y ion plus Y number of moles of B minus X ions. Do you understand this? Right. So basing this methodology, we can calculate the equivalent conductance at infinite dilution of weak electrolyte. As I already mentioned, in the case of weak acid, this is not completely dissociated and does not readily undergo ionization also. So in that case, and this is also the same case. So what we can do, you can do this indirectly. For example, if we apply the Oswald's dilution, and not Oswald's, Kohlrausch dilution law, you can simply put, that is a lambda at infinite dilution of CH3COOH is equal to, you will immediately put ionic conductance of CH3COO minus, and this is infinity, plus you can simply put, that is H plus, okay, at infinite dilution. But this is ruled out. Why? Because they are not readily available in the case of acetic acid. You cannot get complete ionization. But what we are supposed to do, we have to adopt an indirect method. How we can do? We know very well, acetic acid can be split into what? Because this is the weak acid of strong base. Okay, what is this? This is a weak acid of strong base. Strong base is from sodium hydroxide. So this is sodium acetate. So this will dissociate into CH3COO minus and Na plus, for which we can employ Kohlrausch law. Got it? So what is Kohlrausch law? Equivalent conductance of a CH3COO is equal to the sum of ionic conductance of participating ions. That's clear. And similarly, in this case, this is also a strong electrolyte, we can calculate. And this is also a strong electrolyte, we can calculate. So we have got HCl in NaCl. We have split up everything. But you can do some strategy here by adding this first two equation and subtract 3. What you can do, you will get this Na plus Na minus will be cancelled. And what about Cl minus will be cancelled. The resultant is CH3COO minus and H plus. So this is the indirect method. Are you able to follow? So this is the way you can calculate. Okay, are you able to understand this? So this is the indirect method. Now we are able to get CH3COO minus plus lambda m of H plus. Are you able to follow? Which is nothing but this one. But when you try to calculate from this equation directly, you will not get the value. And that is why we take all these values. Now it is possible to find out the equivalent, molar conductivity at infinite dilution of acetate, then HCl, then that of NaCl. By adding this and subtract from this, you can get an equivalent one and you can declare. So this is the Kohlrausch technique. Okay. So why it is called the Kohlrausch independent migration of ion? See, the conductivity is dependent on the nature of the ion, and it's not merely the migration of the ion, and that's why it's called independent migration of ions. Okay. Then calculation of alpha. Alpha is nothing but degree of dissociation. This is a term prescribed for the weak electrolyte. So in the case of weak electrolyte, it is not completely dissociated. So we have to consider alpha. So what is this alpha? The number of moles dissociated. The number of moles dissociated in a weak acid or weak base divided by the total number of moles. In the case of strong electrolyte, alpha is equal to 1. Do you know why? Because they are completely dissociated. When you have got 10 moles, all the 10 moles are dissociated. But in the case of weak electrolyte, this is not so. And that is why in case of weak electrolyte, take down, alpha is always less than 1. By indicating this value, you can claim that this is a weak acid. So when alpha is less than 1, you can declare that is a weak acid. So for such values, alpha can be calculated based on the ion molar conductivity. So alpha is nothing but the ratio between molar conductivity at certain concentration divided by molar conductivity at infinite dilution. And from Oswald's dilution law, Ka is equal to alpha squared divided by 1 minus alpha. Therefore Ka is equal to, in place of alpha, you can substitute this ratio and we can finally get lambda squared mc divided by lambda m into lambda m minus lambda m, lambda naught and this one. Okay, you can just substitute and get the answer. Okay, then Debye-Huckel Ansager equation, which is nothing but, this is applicable for strong electrolyte. So in the case of strong electrolyte, we can apply Debye-Huckel Ansager equation, where we need to consider other parameters. For example, in this case, molar conductivity at certain concentration is equal to molar conductivity at infinite dilution minus A plus B into lambda naught m into square root of C. So in this case, this A, B are the constants, the Debye-Huckel constants, and D is the dielectric constant. Then, and we need to express this A also. So A is given by 82.4 divided by the whole square root of dt into eta, where we need to explain about the viscosity of the, this is called coefficient of viscosity of the medium. So then lambda m, that you know, which is nothing but molar conductivity at certain concentration at 0 means infinite dilution. T, that represents concentration, and you know very well about the what the other parameter, that is square root of C, that C represents the concentration here. Then the variation of generally this molar conductivity with respect to time. For example, in the case of strong electrolyte, when you, for example, you have to reduce the concentration from the infinity, or able follow from the infinity. So let me consider strong electrolyte. As I already declared, the strong electrolyte linearly the conductivity increases, or able follow. So reducing the concentration means what? Reducing the square of the concentration means there is an increase in the molar conductivity, and when it reaches here means it is almost infinite dilution. And what about the weak electrolyte? Weak electrolyte does not readily undergo ionization as in the case of strong electrolyte. It slowly ionizes, then it picks up and it reaches the maximum value. So this position is the what? That is lambda at infinite dilution for weak electrolyte. And what about this position? This is also lambda at infinite dilution for strong electrolyte. So at infinite dilution everything remains the same. Okay, so that is why we had to consider this lambda m is equal to lambda naught m, where lambda naught m is nothing but molar conductivity at infinite dilution minus k into square root of C. So this is almost equal to the similar to this yx equal to mx plus C form, where m is the slope. Okay, so here the x variable and we got the y intercept. So based on that we can consider as two variables, and here it is the negative slope here. Okay.